Question that I do get asked over and over again, and it is something that's kind of important to understand, is the difference between the force of friction and the coefficient of friction. They're very synonymous with one another, which is why it's pretty difficult to understand. So I'm going to try and define them for you here. More importantly, though, trying to explain how we find the coefficient or how we calculate coefficients of friction for different materials in real life, which I think will do a better job maybe of showing the difference, the subtle difference between these two, and then give you like a kind of a more real world example as to why both of these, first of all, are separate variables, but also how they kind of are connected to one another. I think it's easier to see it that way. But anyway, to give you like a basic definition for now, the force of friction, which is a force, a physical force, so we measure it in newtons, it's the force experienced by two, as we say, imperfect surfaces, because there's no perfectly flat surface, when they attempt to or they are sliding over one another. So just realize the force of friction is the actual friction, the actual frictional force that we experience when these two objects are trying to slide past one another. The coefficient of friction is a ratio of that frictional force that we just mentioned in relation to the normal force that the surface underneath, like a box or whatever, is pushing up on it with. Because if you think about it, if the ground is pushing upwards on an object with more normal force, then those imperfections are really going to lock in to a deeper degree, because the ground is literally pushing harder up against the bottom of this block. So the force of friction itself and the normal force itself are related, because when the normal force, when the flat surface pushes upwards on the box or your foot or whatever, it drives those imperfections together. So as normal force goes up, well, the force of friction also goes up. So there's a relationship there, and that's what the coefficient of friction is. It's that relationship. It's a unitless variable, because if you think about it, it's force of friction measured in newtons over normal force measured in newtons. So it's newtons over newtons. It's a ratio, and ratios don't have units. So we give a value like 0.7, 0.5, but there are no units because it cancels out. It's a ratio of two similarly united variables, essentially. Okay. All right, so how in the world do we actually get these coefficients? So what we'll realistically do is we will take two surfaces. Let's say this is surface C, and I don't know, we'll say the block is made out of wood or something. So you always need two surfaces. Those coefficients exist between two surfaces, not just one. But if I were to pull that block across the surface, I would be able to measure the frictional force between, in this case, the wood and surface C, whatever that may be. And I could also measure the corresponding normal force, because in this case, it's going to be equal to gravity, because this thing's not accelerating vertically in any way. So what I could do is I could measure those two, and that's going to give me my first data point. When the normal force is this much, then I get this much friction. But that's just one point. So what we're generally going to do is we're going to take that same block, but we're going to add mass on top of it. So you'll notice here the normal force now goes up, because now you have maybe not twice as much, but more mass is pushing down on the ground, and the ground as a result needs to push up with more normal force. Now that drives those imperfections together, because the ground is physically pushing up to a higher degree on the bottom of this wooden block, so you're going to get more friction as well. So what we're going to do is we're going to measure that again. So we continue this, we add more mass, we measure the new normal force, the new frictional, we keep doing this. We do this several times. Realistically, this is what they'll do in labs all the time when they design like a new tire or some new material. They'll just drag it across different surfaces and measure these, and they'll eventually produce like this table. We have a few data points. When the normal force was this was the frictional force we measured. Now I made these values up, of course, here, but if we plotted this would give us essentially like surface A. I'm making this up here, but that's where these lines come from. All right, those individual dots, the red dots, the blue dots, and the green dots, those would come from measuring the frictional force experienced when a certain normal force is acting on the block. Okay, as you pull these things across these surfaces, you drag them to generate the friction. What I want to point out here, it's not super important that you understand that whole process, but I just want you to understand where this information comes from. The important thing is, if you notice here, the force of friction changes as the normal force changes. When there was no normal force, as you can see in the chart, there was no friction. When there was about 1 Newton of frictional force, I had about 0.2 newtons of friction, 2 newtons of normal force, 0.4 newtons of friction. That's fine. Just understand that the actual force changes. When the object is heavier and there is a more normal force, you get more frictional force. So just realize the actual amount of friction you experience changes as the ground pushes up on you, or the bottom of you, or the bottom of this block with more force. Again, it drives those imperfections together. That's kind of what I tried to show in this bottom left. The leftward portion of that diagram is like when the block is on the ground. The rightward portion is when you add more mass, like in the second case of this diagram where I put a second block, you're going to drive the ground into the block to a higher degree because everything is heavier now, and that's why you get these increased frictional forces. But for now, just understand, while the frictional force is changing, okay, the heavier objects literally experience more friction. If we look at the slope of this line, in this case surface A, the slope, which actually is the coefficient, it's the frictional force of the normal force, it's constant. Even though you get varying frictional forces, right, those individual red dots on that line are different. You get different frictional values. But the rate at which the friction increases in relation to the normal force is constant. That does not change. There's actually only one way to change the coefficient. Change one of these surfaces. Change the block from wood to plastic or from wood to glass. Change surface C into surface A or surface B, or realistically change glass into wood or rubber or cork. If you change one of the surfaces, now you're going to change the slope, you're going to change this coefficient. But if you don't change either of those surfaces, the coefficient will never change. It will be constant for those two surfaces. All right, let me show you a more realistic example because some of this may or may not be making any sense. So the example I like to use would be if, let's say you're designing a new tire, okay? We're going to assume that these tires are going to be used on asphalt, which is a very common paving material. So we have done these tests, right? We dragged these blocks of we took a block of metal and put the tire material at the bottom, okay? And we dragged the rubber tire that we've designed across asphalt, and we have determined that the slope of that graph, the coefficient of kinetic friction when you slide this tire that we've designed or this rubber material over asphalt is 0.64. I just made that up, but here's why it's important to understand the difference. If that is the coefficient between that specific tire and asphalt, that is a number I can use for any object that has that tire and is traveling on asphalt. Same exact coefficient, and that's why it's a powerful engineering tool. So in this case, let's take a look. If I wanted to apply this material for a bike tire, a car tire, and an airplane tire, I can use 0.64 for all three of those cases so long as they all use the same exact tire I was testing to get this number, and they're going to be driving on asphalt. If I change either one of those things, I need to go find a whole new number and recalculate everything. But what's nice here is if I want to use this tire on a bike or a car or an airplane, it's a much more simplified analysis. So first things first, just to make sure we're on the same page, realize that no matter what these three objects are doing horizontally, they could be at rest, they could be accelerating, it doesn't matter. Vertically, assuming the plane is not taking off, while these things are moving horizontally, no acceleration vertically. Okay, these objects are not moving vertically at all, not accelerating. So that's what the free body diagram, at least vertically, will look like for all three. No acceleration vertically means Fn and Fg have to be equal. So I can take a little shortcut. If I want to find Fn, the normal force acting on these three, I just need to find Fg, because since there is no vertical acceleration, going to be the same. I've quickly, okay, you can double check the math, but I quickly just went through and calculated the three forces of gravity for A, B, and C, the bike, the car, and the airplane, mass times 9.81, and I knew that it was equal to Fn. So I now have my Fn. I have the kinetic coefficient, which I came up with through my laboratory testing. Now I could figure out, if I'm on this bike and I try and slam on my brakes, how much friction will I experience? Same for the car, same for the airplane. So just using the coefficient equation, which is mu equals Ff over Fn, you'll notice that for A, B, and C, the coefficient was the same because they all used tire on asphalt. The normal force was different. So you'll notice that in blue, if you're on this bike using this tire and you're riding on asphalt and you slam on the brakes, you'll get about 189 newtons of friction. The car using the same tires on the same asphalt, because it's heavier and because the heaviness or increased heaviness drives those surfaces together tighter, there will be more friction, about 12,560 newtons. The airplane is massive compared to them. Same coefficient if you're using the same tire on the same asphalt, but you get 1.9 million newtons because of how much more tightly those surface imperfections are driven together. What I'm trying to highlight with this example is if we look here, lovely, the force of friction changes, not the same. The coefficients are identical. There's only one way to change the coefficient. Change one of those two materials. That's, I guess, one of the best ways I can represent this. The coefficient is a ratio of the normal force of an object to its force of friction. If the normal force increases, as happened in this case, well, guess what? The friction increases as well because those surfaces are driven together more. So that change, the increase in both, it essentially just cancels out. That's why there's no change in the coefficient. As Fn goes up, Ff goes up. So they rise at the same rate, and that's why this coefficient is constant, because an increase in Fn produces an increase in Ff. But to just try and clarify my original point a little bit deeper, the force of friction, which we physically experience, changes. If I'm a heavier object, I have a different physical force of friction acting on me. But the ratio or the proportion of the normal force or the ground pushing up on me relative to the friction that's generating, that is the same for any object as long as these two surfaces are what are in contact with one another. So just to round this out, hopefully you understand a little bit better, is I guess I could maybe re-summarize in a little bit of a non-technical way that the coefficient of friction, mu, will be constant as long as the surfaces are not changed. Okay, you don't change those surfaces, you might get a different force of friction if you have a different normal force, a heavier object, but you will not change that coefficient unless you literally change the surface. So one way to maybe, I don't know, maybe simplify the definition of coefficient, you could think of it as a property that two surfaces share. And that can be used to determine how much actual frictional force specific objects will experience based on essentially how heavy they are, and then therefore how hard the ground pushes back up on them. But the force of friction is kind of like what acts on the object, whereas the coefficient is like a property that two surfaces can share that dictates how much frictional force a specific object will experience. It's a subtle difference. If you can't tell, it's kind of hard to put into words, but I think a good way to describe it is kind of maybe the way I've tried here. The coefficient is a constant value for two surfaces that allows for the determination of the actual frictional force that acts on an object and potentially slows it down. And the force of friction is the actual quantity of newtons of frictional force that is actually acting on the object. So one is like a property of the surfaces, the other is an actual force that acts on an object and affects its motion. Hopefully that helped. If not, just ask me more questions and yell at me and then tell me that I didn't help you at all. Because this way we can both cry and then we'll both be happy. All right, good luck. Not easy stuff.